So in today's class, we will summarize what we started off last time in terms of the load-based component classification. And we saw that primarily it can be divided into two categories of structures, the one-dimensional and two-dimensional. And we also saw there are certain cases which can be considered as both. And the advantage of looking at it from this scenario is that we can have a single theory and a single way of computing for all of these instead of treating them individually, which is a huge advantage in terms of the modeling paradigm. And apart from the fact that we can treat all of them simultaneously, we can also account for the interactions between them and typically nonlinear interactions between them, which is another huge advantage in terms of moving closer to the reality, which is the 3D in terms of reproducing the results. So when we talk of reliability, essentially we're talking of two aspects. Not the structural reliability that you suggested last time, but in terms of the modeling reliability, we have two aspects. One is the accuracy. Obviously, when you have a model, you want it to be as close to the reality as possible. The other thing is, at the same time, it should not take overly a lot of time to compute. So essentially, the efficiency is of almost equal importance. Sometimes we have applications not only in design but also health monitoring and things like that, where we need almost real-time information, and we are not having access to some supercomputers. It's onboard computers on the aircraft, and these are fairly good, high-end, but still not to the level of supercomputers, which will be an overkill. So with those kinds of computational hardware and software that you're having, are you able to reproduce certain results? And there it's even more challenging, because in a health monitoring situation, you're not only looking at the healthy structure, which is much easier to design and analyze, but also the damaged structure, and you're comparing the current state of the structure with different models to see whether it is damaged or not, and if it is damaged, how big is the damage, how long can the aircraft sustain, and will the pilot be able to land it safely, and if so, how much time they have, and so which is the nearest airport. These kinds of information we want to make available as we go forward. There are already quite a few HUMS systems, health and usage monitoring systems, that we discussed in an earlier class, but their effectiveness is improving, and for their effectiveness to improve, again, these two factors become very important, the accuracy and the efficiency, which is what together we will call as reliability of a model. So let's go ahead from where we left off last time. Here, from the fact that most of these structures, be it the stringers, longerons, the frames, the spars, they are all thought of as beams. Sometimes to start with, you can even think of the entire wing or the stabilizer as cantilevers and the fuselage as overhung, simply supported beams. We saw all of that last time. Now, we can see also the fact that the cover skin and also the web spar, the sparse web, these are all typically the two-dimensional panel-like structures. So it's very clear that if you want to analyze the aircraft or design it, which is the next level in terms of taking the analysis in an optimal sense towards a design, with unknown quantities to start with, which you initiate, and then you go towards the optimal values. In all of those situations, it's very clear that if instead of having a 3D model, if you have a 1D or 2D model, you'll be doing things much more efficiently and quicker, using less resources, even in terms of the human resources that are required. So keeping all that in mind, we need to model, and we need to model it reliably, as we just discussed. So that is the next thing that we will get onto in terms of the dimensional reduction, because it's very clear that it's a real structure is 3D, whereas the you want to model it either as 1D or 2D, depending on the case, and in some cases as both. So when you have such a necessity, it's very clear to see we are starting from a larger dimension and going to a smaller dimension, which is what we call as a dimensional reduction. So a number of dimensions are getting reduced either by 1 or 2. So we end up with one set of theory, which is called as the beam theory, and we allow for generalized curved and twisted beams. In other words, of course, after the load is applied, anyway it will curve and twist, But even before that, even in the unloaded condition, you are allowing for a pre-twist or an initial twist and initial curvatures, which is very common these days, especially in wing tips. You see the curvature over there, and also because of wash in or wash out in the fixed wing, you have the pre-twist. Helicopter rotor blades, the bearingless and hingeless rotor blades have for long been pre-twisted. So for various aerodynamic advantages that they give over the, due to that. And in terms of the structural effects, sometimes these are kind of stress relieving also, depending upon the design. But more importantly, we need to be able to account for that in the model, which is not a trivial thing. It's not like an add-on you can do later on. So while you start with what is known as the very definition of the beam problem in terms of its kinematics, that is in the introduction of the position vectors of an undeformed configuration, of a deformed configuration, how it moves from the undeformed to the deformed, all of these have to account for the presence of an initial curvature and presence of an initial twist, which is what we will do. And the second category of theories is, of course, either the shell or plate theory, depending once again on whether the initial curvature is there or not. So beams, typically people have an imagination straight prismatic. So that's the reason why specifically mentioning curved and twisted, whereas already in the case of the 2D theory, there is a distinction between what is known as a plate theory and a shell theory. So once we mention shell, it is quite clear that there is an initial curvature and twist. So what we are doing over here in terms of introducing this is no different from moving from a plate theory to a shell theory, which is a more generalized sense, because once we set the initial curvatures and twists to 0 over here, the shell theory would essentially become boiled down to your plate theory. Similarly, your if you set the initial curvature and twist to 0 over here, you'll get your simplistic straight and prismatic beam. So either of these cases, because of the fact that we are moving from 3D to a lower D, there is going to be an increase in efficiency, and typically it's of the order of 10 power n, where n is the number by which you're doing the dimensional reduction. So if you're going from 3D to 2D, you're reducing it by 1 dimension. So typically the order of magnitude savings in your CPU time, if you implement the algorithm appropriately in your coding, etc., it would be of the order of 10. Whereas when you're moving from a 3D to a 1D, you're reducing it by 2 dimensions, so 10 power 2. So you typically will have CPU savings of the order of 100. And this, as I have been saying earlier, gets a multiplying factor when you're going for repeated application of this code for a particular application. It could be either optimization, design, or health monitoring, where you're comparing between two different kinds of models. One is the healthy and the other is the damaged, and the actual structures, information that you're getting from the sensors, etc. So the fact is quite clear that you get about 10 to 100 times improvement in the computational efficiency, but there is going to be a drop in accuracy. You have to live with it, because this is the reality and this is what is your model, and quite clearly it's not the reality. But if you do this process appropriately, as I've been repeatedly saying, this drop in accuracy, it cannot be 0, but it can be minimized of the order of 1% or lesser. For all engineering purposes, it might be same as your 3D theory. So the main advantage you're getting, of course, is in a 10 to 100 times savings in your CPU time. So are there any questions or doubts about this? We'll move on to a next topic otherwise. Yeah. So now we look into material selection. So material selection, again, it could be the so-called conventional materials, which is the metals. It could be ceramics. It could be in certain locations. It could be polymers, or combinations of these, what we call as composites. So composites could be combinations of 2 elements from any one of these 3 baskets. So generally, materials can be classified into these 3 categories: metals, ceramics, and polymers. And between these, you tend to choose. So there are examples of polymer composites. There are examples of carbon-carbon composites, which is ceramic, and there are also examples of metal matrix composites in which the fiber could also be a metal. So, and sometimes even the same material could be drawn in a fiber form and put in a same matrix. Carbon-carbon is an example, but there are a few other polymer examples also for that. Some polycarbonates can typically be drawn into fibers where they have much greater strength and stiffness in the longitudinal direction parallel to the fiber compared to the bulk material, which is the matrix into which they are placed. The advantage of such similar material for both the similar or same material for both the matrix and the fiber is, of course, the compatibility, because that's one of the things you need to check when you're choosing your fiber and matrix, is whether these two are compatible with each other. And compatibility is, one is of course mechanical compatibility in terms of the surface roughness and how they fit into the matrix. The other is the chemical compatibility. They should not be reacting overly. Even if there is a reaction, it should actually be a stabilizing reaction where it stops after a certain layer of coating is formed, and that makes it even better than what it was originally. And certain other physical principles, and also we discussed in an earlier class the possibility of galvanic corrosion, which means that they have to be far apart in terms of their positive and negative natures in the electrical sense or electrochemical sense. So, keeping all that in mind, of course, when we do the material selection, even for small aircraft, a single material won't do. So you'll have to go component by component. For the spar, again, for the spar web or the spar cap, you might use different materials. For the stringers, you use different materials. Skin, you use different materials. Bulkhead, etc., depending on the requirements over there, because we know the typical loads that are coming on each one of them, and therefore the maximum stresses that they are encountering. Of course, it will be a mixed set of stresses, but there will be one or two dominant kinds of stresses. Some might be facing more normal stresses, some might be facing more shear stresses. If you look at the previous slide where we had the 1D models and the 2D models, typically in the 1D scenario, mostly it will be normal stresses, either coming from axial loads, tensile or compressive, and bending loads, which are also going to be shared between, let's say, a top stringer and a bottom stringer. One of them will be taking only tension, the other will be taking only compression, and therefore you're essentially seeing that there is a normal stress which is dominant over there, whereas in the shear webs or the cover skin, etc., the shear, as the very name suggests, these are shear panels, and therefore shear would be the dominant thing. So when you do this material selection, obviously we'll look for superior material properties in shear for such applications, and for the former applications, superior behavior in tension and or compression. Some might be subjected for more tension compared to compression. Very clear distinction in the case of the top surface of the wing and the bottom surface, whether it's the cover skin or the stringers associated with it or the spar caps, there is a clear distinction. So very many cases you will see different materials being used for the top and the bottom of the wing. We will have many different criteria. One is, for example, corrosion. Apart from the galvanic corrosion that we already discussed, there's also regular chemical corrosion, and one because of the kind of environments that it is exposed to, especially if it's operating, let's say, on aircraft carrier, the kind of salty water scenario that you have over there. If it's operating in higher altitudes, the kind of exposures that it gets, the kind of exposure that it gets in certain regions where probably it's helping with the oil transfer and things like that. So the oily nature of the atmosphere and possibility of oil spillage and things like that. So many different corrosion criteria, fatigue criteria, impact criteria, all of these need to be checked, which is far more significant than the other, and based on that the material selection will be done. But predominantly from the load bearing capability, these are the three criteria that are most important and primary criteria that we look at, but it will be subject to the constraints of all those other things that we discussed, like corrosion, fatigue, etc., which will also be brought in at a later stage. If you have a shortlisted set of materials which fulfill this criteria, then you will check for the other more advanced kind of behavior that is required, and you would drop off some from the short list and eventually arrive at what is the most promising material that is there. So in addition to all these technical aspects we already discussed, there are the possibility of availability of that material, the cost of that material, and the ability to continue procuring that material for replacement parts later on. So all of these also are typically taken into account because costing is a very, very complicated thing to actually do, because one is the initial raw material cost. Then you're taking that raw material and making, let's say, a spar web out of it. That fabrication process or manufacturing process involves certain complications, which is dependent, it changes material to material. Some materials might have a very high initial raw material cost, but it could be very low in terms of the production cost. The others could be opposite, and there could be some which are both high or both low, etc. Depending on that, the cost constraint that one has, typically decisions are made on that. Typically for large scale production, when you have, for example, when you're making an aircraft for, let's say, airlines, passenger aircraft, you have large numbers to probably cater to. So that scales also matters in terms of reducing or increasing sometimes your production costs. So you have to take into account that numbers that eventually you probably will produce as well. That also comes into picture. So while we are aware of all those things, we'll not get into the details of those things. We will get into a little more detail of the strength, stiffness, and stability based design. Again, we will not go into the rigorous model that I talked about in the previous slide. We will use very simple models that you are already familiar from strength of materials to understand the relevance of these three and what kind of information or criteria they give us for the material selection. Later on, because this is purely to select the material, once the material is selected, then the geometry, etc., all those things we'll see if we can do it with the higher and more reliable models, the more accurate models. So just for the understanding of the material criteria, selection criteria, we will go for simpler models over here. Okay, so first of all, it's very clear that out of the two important aspects of a structural design, one is geometry, which we will go into later on. In fact, we saw various aspects of it already in terms of how they can be beam-like or shell-like structures, one dimension being very large or small compared to the other two, and also how they are eventually joined to each other, etc. So that is one aspect of it. The geometry purely, of course, the outer geometry is dictated by the aerodynamics, but the inner geometry is entirely our prerogative as structural engineers or structural engineering teams to look at what is the thicknesses of each one of these materials, what is the actual cross-sectional shape, which out of the many different open or closed cross-sections that are possible, which do you choose, and all those things. So that is one aspect. The second aspect is this material selection, which is almost as crucial as the geometry selection. So the physical properties of, if you take the most commonly used three material systems, in particular the metallic alloys which were used for a long time and continue to be used, we will look at those. There are of course innumerable number of physical properties in terms of their optical abilities, their thermodynamic abilities, etc. But we are focused purely from a load-bearing aspect, certain properties of interest for our choices. So let's look at that. So typically, again, in terms of these metals, rarely they are used in their pure form. They are all alloys. So you have typical aluminum kind of alloys, what are known as the 2000 series and 7000 series. We'll go into a little bit of details on that, of what those codes mean and what those distinctions are. Right now, we will club them all together into a single quantity we'll call as aluminum alloys. Similarly, titanium alloys, again, there are many, many different kinds. Some are more commonly used with aerospace applications because they are qualified as aerospace grade by the certifying agencies. So titanium alloys, and similarly, again, of course, steel, all of you are familiar that there are many different kinds of steel, and in particular, they can have extremes in terms of some which are very high stiffness but low strength, and some very high strength compared to other steels, but lower in stiffness. So there is a possibility of that. But the range of stiffness variations is not much within each one of them. It is more the strength that goes through a huge variation. Depending upon the alloying elements you have, but there can be exceptions to that rule as well. So out of these three materials, the first important property that is quite clear is in tension. What is the ultimate strength, what we call as the UTS, or ultimate tensile strength. For applications where tension is the dominant load, it could be, for example, the bottom skin, or it could be the bottom stringers, or the bottom spar flange or cap, whatever you want to call it. So those cases, this is one of the important things that you'll be looking at. Of course, many of these metallic alloys will go through yield before they get into the actual failure, and so the yield criteria might become very important as well. And for ductile materials, usually the failure will be in a shearing sense. Even UTS tests, you would see that compared to these metals, which will mostly fail at a 45-degree angle, even when you're applying a uniaxial tensile test. Whereas for composites, in many cases, because it's brittle and all the way it directly fails without yielding, you would see that the cut is typically almost perpendicular plane to the length of the specimen that you're trying to pull apart. So keeping all those differences aside, and again, because there's such a wide range of each one of these, there will be a wide range of these values as well. We are just taking ballpark values approximately to our only purpose is to compare them with each other rather than within themselves, which we will take upon in a later stage. So and this is typically given in megapascals as opposed to stiffness, which we shall see later on, which is typically specified in gigapascals. It's quite clear that the failure strain is of the order of a few percentage, and therefore it makes more sense to have reasonable numbers that you can remember in the case of the strength in terms of megapascals and the stiffness in terms of the gigapascals. Because the strain of failure is of the order of a few percentage, typically the ratio of this is of the order of 100 in terms of orders of magnitude if you're talking about, because if it's 1%, obviously the ratio is 100. If it is, of course, linear all the way, which it isn't. It is linear somewhere close to the yield point, and then it has a non-linear regime, but we are only talking of orders of magnitude over here, so typically you have of the order of 100. So now it's very clear there's a huge distinction between these, and if you're looking purely at the absolute strength as the criteria over here, then very clearly steel is a winner by a huge margin compared to both the other materials. But we know that in aerospace applications, not only now but in the past as well, aluminum has been used quite a lot, and we gave hints to this in the very first class where we talked about not the absolute values but the specific values, which is what we are heading towards here through a very simple derivation process instead of just stating that, which is what we did in the first class. So it's also the ratio that you have to remember, approximate ratios. So almost 3 times is what you have as titanium, and from titanium to steel, it's almost double that you're essentially looking at. So that is the order. As I repeatedly keep saying, these are all huge ranges, so the actual ratios might also have quite a variation, but these are certain things to have at the back of your mind to understand how they are relatively in terms of each other. Even though we're moving a lot towards composites, both in terms of weight fractions of about 50% or more, and also volume fractions of about 70 to 80% in many passenger aircraft, apart from, of course, the fighter aircraft and helicopters, which have been already pioneers in terms of application of composites much before the passenger aircraft started this trend. So the next thing, most important thing, of course, in terms of the physical properties that we are discussing is, of course, the Young's modulus, which, as I said, is typically stated in gigapascals. And here, there's not too much of a scatter. So around 70, 73 is what you see for most aluminum alloys. And also, again, all of these values we are giving in tension, whereas sigma U can vary quite a bit in tension and compression for for the same alloy, E will not vary so much between tension and compression. There is a slight variation, but not something to be too much bothered about. And 3 times that is the value of steel as Young's modulus. These are problems that you would have come across quite a bit preparing for gate, etc., where you typically have bimetallic strips, etc., made out of these, and how they behave under different kinds of loading situations, etc. And just like in the case of sigma U, titanium falls somewhere in between these two. And the dominant reason why titanium is used is in terms of high temperature applications, and also sometimes corrosion related reasons. So that's the reason, and also because it's also not only in between, but also in terms of the costs, it is amongst the highest. In terms of availability also, it may not be, aerospace grade titanium may not be so readily available as your aluminiums and steels, which are much more available around the globe. So it's very clear both from the sigma U criteria as well as the E criteria that in terms of absolute values, steel is a winner by a huge margin, because sigma U of steel is much larger than that of aluminium as well as titanium. And in turn, also the Young's modulus, the same thing is there, that E steel is much larger compared to E aluminium and E titanium. So this is the overall conclusion in terms of what we are looking at out of these 3 categories of metals, which are very commonly used, have been for a long period of time in the aerospace industry. So now it's an obvious question which all of you already know the answer for, both from your prior background as well as what we've been discussing in earlier classes, that steel is the strongest and stiffest in an absolute sense, but still it is not preferred always, because the weight becomes an important criteria, and weight is not a material property. Instead, we have to look at the mass density, how many kilograms per meter cube each of these alloys weigh, and then we have to come at criteria which takes care of that. So once again, we look at these same 3 sets of metals, aluminium, titanium and steels, and in each one of these we have to look at the densities. So aluminium is of the order of 2,700 kilograms per meter cube. Once again, steels are the largest in this, but it's a property that we want it to be smaller rather than large compared to the other 2 properties that we saw, where bigger is better, here smaller is better. So once again, titanium falls somewhere in between, so 4,700 approximately. So again, as I said, it could vary between specific kinds of each of these alloys. So we are only looking at relative values over here. Now, quite clearly, the question that has been asked is in terms of why steel is not preferred. It's obviously the what we saw in terms of the numbers per row density, that it is far heavier. So aerospace is a weight sensitive design. There are many other weight sensitive designs as well. For example, your Formula 1 cars or the Formula cars, these, and typically many moving structures, you would want to make it more efficient by reduction in weight. And the higher the speed, the more payoffs you get by reducing the weight. So typically, for example, if you're looking at in terms of how much of reduction you can have for, let's say, a re-entry vehicle that ISRO is working on right now, you're going to have a much larger cost saving by even a small reduction in weight. The same small amount of weight reduction for, let's say, a small aircraft, a 1-seater or a 2-seater trainer, let's say, is not going to make that huge a difference. And when you're talking of costs, again, always I want you to keep in mind the initial material cost, the production, and here also the life cycle cost, because certain maintenance might be required, certain materials might go through more corrosion, etc. So you might have to do coating and things like that. So all those have to be taken into account as well in terms of choosing a material for a particular component. And here we are not talking of the whole aircraft, because we know that the whole aircraft consists of many different materials. We are talking of component by component. So in a weight sensitive design, you have to do a compromise because it's very clear from the density point of view, aluminum is the best, and from both the Young's modulus as well as the tensile strength point of view, steel is the best. So you have to look at something to a criteria which can take care of both of these in a weighted sense. So the need is there to compare the material performance for specific structural applications. So, and when you're talking about it, we're not talking of application of aerospace as a whole, but you're looking at applications of each structural component. So how do you choose the material for the spar cap? How do you choose it for the spar web, etc.? Quite different from each other. So there are three primary categories of design situations, and doesn't mean that one is the only important for a particular component, the other two are not important, but in terms of priorities, one takes over the other in different kinds of situations. We have discussed, for example, where dimensional stability is very important, where you're going to put an antenna and the connecting structure which connects to the antenna, that has to have a much more dimensional stability compared to let's say an aircraft wing, which is allowed to deflect by a large amount. So you may not give an overkill of stiffness over there, which is not necessary, because in terms of the aerodynamics it may not affect it too much, but at the same time, if you do it, then the weight penalty will be humongous. So you would want to deal with something else in that case. But nonetheless, it's important for us to know all these three. Yes. Yeah. Uh-huh. Exactly. We'll come to that. So in fact, it's a myth that steel has a lower sigma U by rho or E by rho. It is sometimes almost on par with the others, or sometimes even higher. And so that is not the primary reason why steel is not used. So you're absolutely right. Good that you calculated it in between. So we'll come to that. There are other reasons. One of course will be the corrosion resistance. So steel is typically subject to rust. And of course, not that aluminum is not subjected to corrosion. It's subjected to corrosion, but what happens is, as soon as you make it, it reacts with the air, oxygen in the air, to form an aluminum oxide layer, which is almost uniform. Whereas the rust is also kind of an iron oxide you're looking at, but what is happening over there is that the typical volume of that is much more. So what happens is it doesn't stick to the surface, it just comes off like this, and therefore usually it falls off, or it exposes, more importantly, the rest of the steel also to the corrosion, and therefore the corrosion starts going deeper and deeper. So that is essentially one of the things. There are a few other things also, but it's an excellent point. So if you're comparing just between the metals, steel probably has a reasonably good specific values as well. It's not just the absolute values. So we will look at these strength, stiffness, and stability criteria. But as I said, based on this discussion also, these are not the only three criteria. These are purely from the load carrying capability, but there are others as well. Stability is, of course, associated with buckling. It could be associated with the aeroelastic instabilities like flutter and or divergence, etc. So that also brings in certain requirements, both from the geometry point of view as well as the material point of view. So these also, in terms of the overall strength of a structure, the geometry also plays a role into this, but we are trying to isolate from that just the material properties and see how we can compare one material across the other. We are essentially making this design decision twofold. One is the material-based decision, the other is a geometry-based decision. So right now we are focusing on the material-based decisions. So let's move ahead. So we need to, of course, because these are three important criteria from a load bearing capability point of view, the material performance index needs to be derived for each of the above three S's, that is strength, stiffness, and stability. For each of them, there is a separate material index that we will see. In fact, we've already seen what it is in the case of the strength and the stiffness based design, sigma U by rho and E by rho, but we will have to derive it specifically for those two cases, as well as see what it is for the stability case. Okay, so this is a picture that we will probably use often in the rest of the course, where we take either, let's say, a sheet metal or a composite laminate, typical of, let's say, cover skin or the shear web. It could also be a stringer for all you know. So which could have components made out of this. For example, if it's a Z section, it can be thought of as 3 separate strips like this which are there. So each one of them you can treat it individually, where you have a rectangular cross section. You could have in general an initial twist and curvature. The curvature is not shown over here, but the twist is shown with a 3-dimensional effect over here, which is why when you introduce these unit vectors, first of all, we have these coordinate curves. One is x1 along the length, and the length we call it as L, as we did in the previous class as well. Then we'll have along the width or breadth, we'll have the dimension B for breadth, and we will introduce the coordinate curve x2, and we will introduce a coordinate curve x3 along the thickness or height direction, which height we refer to as h, and we will continue to use that terminology going forward. Now, if there is a pre-twist as is shown in this particular picture, a small pre-twist, then it's quite clear that the unit vectors which are tangential to these coordinate curves are going to be functions of x1. And if there is an initial curvature which is not shown over here, then you would also have B1 also as a function of x1. If it's, you can very see if this is going to be curved like this, then at each cross section, see that the vector coming out of that cross section perpendicularly is going to be something that is going to be a function of x1. Now, in the undeformed configuration, the way we define it is that the perpendicular to the cross section and tangential to the reference curve is one and the same. But after deformation, these two can change, which is what is a violation of the simple engineering beam theory that you have gone through, where in the Euler-Bernoulli beam theory, you say that not only plane section remains plane, but also anything which is any line which is perpendicular to the cross section remains perpendicular even after deformation. Now, we allow for that to change, which is what Timoshenko also did in his theory to introduce what is known as the transverse shear strain. So these are important things to measure, and remember, I'm talking about these as coordinate, not coordinate lines, coordinate curves, because for an initially curved beam, your x1 curve can be curved, and which means you're in general open to what are known as curvilinear coordinates instead of rectilinear coordinates. What you're usually used to in drawing 3 orthogonal axes or straight lines, x1, x2, x3, and the unit vectors b1, b2, b3 parallel to them. Those are situations where b1, b2, and b3 do not change with x1, and you have x1, x2, x3 curves not as actual curves but as straight lines. But here in general it is possible that these are curved. You know that typically you're dealing with curved surfaces because of the airfoil and the other things that you have in terms of the overall plan form, how it is constructed, the sweep, the taper, etc. So all of that has to account for. Here for simplicity you're showing a constant cross section, but the cross section can also change as you go forward in terms of at different locations. But here our goal in this class is just to derive these material performance indices, which is what we will do using very simple models, and also we will take a very simple structure. So here we'll take a simple prismatic structure. We'll assume there is no pre-twist in this. We will apply very simple loads. In general, there can be all kinds of loads coming on each structure, while whereas one of them or two of them might be dominant, but still in general you could have non-zero values for all kinds of loads. That the tensions in the 4 directions, the 4 directions on the 4 edges rather, and you could have tension or compression, and then you could have the shear on them, and on the surface, both on the top as well as the bottom, you could have pressure distributions and or shear distributions as well. So all of that can happen in general. But right now, let's focus, let's say, on the bottom cover skin as a panel over here, a straight panel. A very large aircraft, if you take a single panel would not be looking more like a shell, it would be looking more like a plate, a very thin plate or panel as you call it. So suppose it is that kind of a situation. Of course, there are certain boundary conditions we need to deal with, but here we will take, for simplicity, these two edges are free, one end is fixed and the other end you're trying to pull. It's a very simple bar example, the bar under tension that you're all familiar with. So I want to keep all these things simple just to get the material criteria, but we will go into more detailed ones later on. Yes. These are unit vectors, B1, B2 and B3, which are tangential to the coordinate curve. So what you do is you first take a beam, it could be curved in general. So you introduce along its so-called length, you introduce a coordinate curve which is called as x1. So any particular value of x1, let's say 2 meters, will fix a particular cross section. On that cross section, once you take that cross section, you need 2 coordinates because it's a 2-dimensional surface. So you introduce 2 more coordinate curves, x2 and x3. So many situations you would not need curves over there, straight lines would do, but there could be certain shapes where it might be from a mathematical perspective, derivation perspective, it might be more convenient to deal with curves. So for example, if the edges of that are curved, so you might want to keep the coordinates also curved to match that kind of a thing, something like this. Yeah. So something like this, if this is the cross section, I'll just come to your question. So if this is the cross section, sometimes it might help for you to introduce a coordinate curve like this, or if it's a circular tube, for example, very, very clearly you might go for an r theta kind of a system where the theta coordinate is obviously a curvilinear coordinate, right? Yeah, you were asking something.
All the 3 curves will be orthogonal at that cross section.
That's correct, yeah. So it is, it's not a necessity. You can have a situation where these are not orthogonal to each other, but the requirement is that they should not be coplanar. So they should all 3 not lie on the same plane, in which case you will not be able to take into account the third direction at all. If they are at non-90-degree angles to each other, still in terms of those 3 coordinates, any material point can be identified. But for most practical purposes, orthogonal coordinate system is what you require. And it could be, it is also orthonormal in the sense that B1, B2, B3 are unit vectors. Okay. Yeah. So let's go ahead. I think I've talked enough about this. Yes. So here for the strength-based criterion, material failure is the criterion, obviously. Of course, yield and other things have to be brought in, but right now we're keeping simple, doesn't matter what is the specific criteria, particular quantity we are taking. Let's choose sigma u for here. Let's say, for example, if it's a brittle material, then that's what it would be. If it's a ductile material, then you have to make appropriate changes. So consider this sheet under tension. It could be, let's say, a composite laminate, for example. So if you consider this sheet under tension along the x1 direction, so we have a, based on what is known as the Saint Venant's principle, which you have probably gone through, you have the so-called end effects very close to the boundaries where an attachment is made or a load is applied. So those regions, typically you will require a 3-dimensional model. Just for the sake of fitting it into this board, you are seeing that it's shown fairly compact, but typically these will be fairly long structures, and the length will be very large compared to the breadth as well. And so in such situations, what you will have is typically for a beam, it will be either B or H, whichever is the larger of the two. Of that order of magnitude, typically 3-dimensional effects will be dominant, and from both the ends, and if these ends are fixed as well, from that end as well. But if you're looking at a plate or a shell model, which you're reducing it to a 2D model, then it's of the order of the thickness. So which is what this case is. It's like a sheet metal or a composite laminate, where of the order of thickness or a few thicknesses you would have to deal with in a 3-dimensional sense, because your 1D model, however well you derive it, will not give you good enough results, especially if you're interested in damage and things like that. Another critical thing that I remember at this point of time, though it's not associated with this, is in terms of lightning protection. So when you look at lightning protection, many of the metal aircraft, you do not have too much of a problem. But when you go to polymer-based composite aircraft, you typically will have that as an issue, especially if you have carbon fibers, because carbon fibers are very good conductors of electricity, and the matrix that they are put into, epoxy or whatever, is typically a very good insulator. So what happens is sometimes these panels are joined to some other panels through, let's say, a bolted joint or a riveted joint, which is also a metal. And that will perhaps go through a carbon fiber or something, and that becomes a path for the electric signals to travel much easily compared to any other path, and therefore that can cause very huge voltages, and it can cause disasters. So typically you have very fine copper meshes which are typically put in between the layers, and which are typically in connection with the fibers, so that that becomes the path, and it's a much more even distribution rather than through a particular fiber or a set of fibers or a toe. So that is something that needs to be taken into account also during your structural design when you're choosing the material, the kind of joining technology. So you would prefer probably adhesive kind of joints rather than those joints, or if you have those joints, you have to ensure certain things precautions are taken. In addition, of course, you have these lightning protection mechanisms. So coming back to our problem, we are considering a uniform stress distribution in the interiors, because only close to the edges the end effects would be there. In the interiors, we can assume that it is uniformly distributed. So I might be applying my tension as a so-called concentrated load or a very intense load only close to the center, or I might uniformly distribute it, or I might distribute it linearly. However I might distribute it, it just doesn't matter. Once I go a few orders of the thickness into the interior, it's equivalent to distributing it equally. Because there, if I cut any cross section and draw a free body diagram, the stress that is there is offered by all the material points of that cross section equally, and that is equal to, of course, whatever the load you're applying divided by the cross sectional area, which in this case is a simple B into H for a rectangular cross section. So the total load carrying capacity, if you take, that is, I apply a load P, I fix that end, keep these two edges free, and I keep on pulling it and increasing the force with which I pull it. So there is a certain value of the force at which this is going to fade. So that we call as the load carrying capability of this structure. So it has to obviously depend upon the geometry, but in addition, it also depends on the particular material you have chosen. What is that material property is what we are trying to look at from a weight sensitive design perspective. So the total load carrying capacity is obviously the maximum P, or the force P that I'm applying here. The maximum P is going to be when the material is going to reach the ultimate tensile strength of this particular material. So that, let's say that is sigma U. So it has to be multiplied by the cross-sectional area, which is BH. In reality, what will happen is there's a certain thinning and other things that will happen. So we are ignoring all of those effects over here, just keeping things simple. So because the geometry is not of significance here, the material property is. So sigma U, which is the stress or the maximum stress that this is capable of, multiplied by the cross-sectional area, which is B times H. So let's call this equation 1. Now, because it's a weight sensitive design, I'm not only interested in its maximum load carrying capability, I'm also interested in its mass, because remember, we talked about at the beginning of last class in terms of the structural history. There is a certain weight allocation which is given for the structural components, which is typically in today's technology of the order of 20%, which is about 1/5 or so. So within that, we have to make all of these skins, the spars, the stringers, the bulkheads, etc. So we have distributed amongst that, and for this particular component, we know what is the maximum allowed mass that I can take. If it is lesser, better, but there's a certain cap beyond which you can't allow the mass of this component to go to. So the total structural mass is quite obvious. It's a cuboid structure that you have. LBH is the volume. So that volume multiplied by the density of the material that we are going to choose. So that is, if we call the density as rho, using the same notation that we used in the previous slide. So the mass becomes rho times BHL. Now we want to combine these two equations and eliminate certain geometric parameters associated with it. What are the geometric parameters we can eliminate? Those parameters on which we can make structural decisions later on, because as I said, structural design involves two aspects: material choice and geometry choice. In the geometry choice, I'm going to make decisions on the thickness. I'm also going to make on how many panels I'm going to have, each panel how much width it is going to have, because the entire cover skin of the aircraft, let's say, I can make with multiple panels, and each panel can be treated as a separate structural component and how it is joined to each other. Here, of course, I'm ignoring the boundary conditions on this, but these edges are joined to adjacent panels, and that boundary condition has to be taken into account as well. And of course, the loads are much more complicated. It's not just an axial load that you're applying here. There are various other complications coming in terms of pressure, etc. But we already saw that the primary thing is the bending, and therefore the bending is predominantly the bending stress that is going to act on the bottom surface. It's going to be a tension, and that tension is what we are talking about over here. The stress on the surface, which is your sigma 33, considering this same coordinate system, would be much smaller compared to your sigma 11. So sigma 11 is the dominant stress. So between these two equations, there are certain geometric decisions that I have to make on the thickness of the plate or shell that I have to carry, the panel, which is appearing in both these equations, H, and also the breadth of that panel that I'm going to take. But the other aspects, there are material properties over here, and there is also an L, which is the overall length of this, which is in terms of the spacing you typically have for the ribs, for example, which is also a structural decision. But if it's a small aircraft, it could be the entire span of the wing, in which case it's an aerodynamic decision. So that's that depending on the case by case situation, L may or may not be a structural decision to make, but most cases H always will be a decision, and B in most situations will also be a decision that you're making in terms of the number of panels and how you're attaching them to each other. So between these, we will eliminate those geometric decisions that a structural engineer will typically make, in other words, BH. So we can eliminate BH between these two equations to give your P max, the maximum load carrying capability of this, as the mass per unit length times the sigma u by rho. And this is why we, in the very first class, we refer to this particular parameter as an important material parameter to discuss when you are doing a strength-based design. It's not the absolute strength that are important, because it's a weight critical design. It is sigma u by rho which is important. The other things are geometric decisions, and here also M is what is the mass which is allocated for this particular component, and L may or may not be the criteria. In any case, it's not a material property. The material property what you have is in the second bracket over here, which is your sigma u by rho. So for a given mass and geometry, therefore, it's very clear that by given mass, of course, we mean what we have allocated for that particular structural component, so that the total mass of all the structural components put together will not exceed about 20 to 22% of the overall maximum takeoff weight of the aircraft. So P max very clearly is therefore, in terms of purely material properties, proportional to sigma u by rho. That is the therefore the material performance index as far as a strength-based design is concerned. So again, depending on component to component, what kind of loads are there, what kind of boundary conditions are there, and what kind of material it is, whether it will yield, etc. All these things can change. But essentially what we are saying is some kind of a limiting material stress capability divided by the density is what it will eventually depend upon if you remove all the geometric dependencies from it, and also the mass allocation from it. So that is essentially what we are looking at through this simple example. You can do this for various other examples and see that you will arrive at somewhat similar criteria. Instead of the ultimate tensile strength, it could be the yield strength. If that is the criteria, it could be the, let's say if it's primarily a shear kind of a problem, it's the shear strength that you'll be looking at. But essentially, it's this kind of a ratio that eventually you'll be coming. This is just a sample that we are looking at using a lot of assumptions that we are making over here in terms of ignoring the boundary conditions over here, in terms of ignoring the end effects, looking at only the central portion. In reality, it is this portion that we should be more bothered about, because that's where probably because of the end effects, there's a possibility of stress concentrations and the failure might actually occur there, etc. But that's all for another day. We just have to look at the ballpark values from a more simple model, just to understand how the material influences the overall design. So instead of dealing with the same structure for the stiffness based design, let's take a different kind of a structure, because there's also an opportunity to introduce different kinds of structures which are commonly used in aerospace industry. So instead of a sheet metal or a composite laminate, let's take a sandwich construction, and instead of applying, let's say, an axial load, let's apply a pure bending moment for the second example. So once again, the geometry is the same. The length is L, the breadth is B, the overall height of this structure is H. Once again, you consider a cantilever kind of boundary condition. So we fix one of the ends, the other end that we apply a tip moment, it's a bending moment about the x2 direction. So we call that as M2. So for this M2 that is applied, we want to see if we want to either minimize the deflections, which means that the curvature that you're going to end up with, because the primary effect of a moment is the curvature that develops, and so either you want to minimize the curvature, or to make things a little more advanced over here, we will not look at a static design but a dynamic design. In a dynamic design, what you typically do is there are many things that you need to control. One of the things is the natural frequencies of this particular material. In particular, because for this load, kind of load that we are looking at, we will be interested in the, when there's no load applied, what is the bending natural frequency? And again, there'll be many different modes for that. In the first mode, what is the bending natural frequency that you have? So that will be one of the criteria to for design, because the loads are also dynamic in nature. Let's say the air loads, the gusts that come in, or loads coming from other components, etc. They all have certain frequencies which are known either as a deterministic value or as probability density distribution functions. You know a certain range in which all those loads are the dynamic loads. So you want to make sure that the natural frequencies of your structural component, which is exposed to those loads, is not close to those loading frequencies. And those loading frequencies, so typically in most designs what you do is, if possible, you try to put it above those frequencies. There's a certain range of frequencies, because most of these loading frequencies are low frequencies. There are very few very high frequencies, but low frequencies is the dominant load that comes in many situations. So what you're interested in is in going beyond those frequencies. In other words, you set a certain minimum benchmark for your natural frequency, the first bending frequency over here, and you try to design the structure to be there. And you know, from even single degree of freedom systems, when you just have a mass spring without even a damper, you have a spring of spring constant, linear spring constant K, and a mass M. You have the natural frequency square root of K by M. So quite clearly, it is the stiffness which dictates that. In that case, the stiffness of the spring, and there's a mass which dictates that, which when we extend to a continuous system like this, obviously is going to be some kind of a density associated with the structure. It could be a mass per unit length instead of a mass per unit volume, but essentially it's a density which is associated, which has certain material properties and or the geometric properties of, let's say, the cross-sectional area, etc. Another reason why I introduced this is, we talked about it earlier, that typically in a structure, though for this example we have taken just the load as the tip bending moment over here, really the way the bending moment actually comes is through a distributed force that you have over here, and the primary effect of that distributed force of course is in a bending moment diagram, and therefore the normal stresses which come out of it. But in addition, the transverse loads, whether concentrated or distributed, are also going to bring in transverse stresses, which are shear stresses on any given cross section. And it is this intermediate thing, layer, which is your core, which could be made out of a honeycomb kind of a construction with aluminum, etc., or it could be a foam of different materials, that will be capable of taking. And typically for a rectangular cross section like this, that shear distribution will be parabolic like this. In other words, it will be 0 at the top and the bottom to satisfy the boundary conditions on the top and the bottom, because complementary shear stresses are going to be 0 for non-magnetic materials, which these are, and therefore you would have 0 at the top and the bottom. It will reach a certain maximum value at the center, and these materials should be good at taking shear. But in terms of the bending stress that is going to come, that is much more. We will compare those orders of magnitude in a probably next or class after that. But essentially that is going to be having a linear kind of distribution, going to 0 at the neutral axis, and going to, in this case, the way that moment is shown, compression at the bottom and tension at the top. So that's where you want to maximize your tensile load carrying capabilities, and on the top, and bottom you want to maximize the compressive load carrying capability. So if you choose 3 different materials for this, you would choose a material which is very good in tension for the top, very good in compression for the bottom, and for the core you would choose a material which is very good in handling transverse shear. So that's essentially how you would go about doing it. Another reason why I took up this example over here is that there are certain small parameters which are associated with this system. Even in the previous thing, we saw that if it was a plate, H is very small compared to L and B, the length and the breadth, in the previous sheet metal example for the strength-based design. So similarly, you also have, if it's, let's say, a beam, then even B would be small compared to L in that case. Now coming to this example, in addition to L, B and H, which is the overall height of this, there is also the individual layer thicknesses of each one of these. So the top and the bottom are called as face sheets, and the in between is called as the core. So that overall H, which is the height of this structure, if it is divided between T, which is on the top, it could be T1 and T2 for different thicknesses in general, but let's say T, it's of the same order of magnitude. Those T's will be much smaller compared to the height of the core that you have. The core thickness will typically be much larger, and all for right reasons. We'll look at some of those later on. The very simple thing to see is that in terms of that parabolic distribution, it doesn't fall off drastically from the maximum that it is at the neutral axis. It doesn't fall off drastically. So there's a fairly large thickness over which the transverse shear can be resisted by this material. So it makes sense to have that as much larger compared to the face sheets, which are very good at tension and compression handling. So, in addition to H being small compared to B, B being small compared to L, overall dimensions, you will have T small compared to H. That is another geometric small parameter you're going over, looking at over here. Another material small parameter you can look at over here is in terms of the Young's modulus of this material divided by the Young's modulus. If it's a laminate, then some kind of an equivalent Young's modulus along the longitudinal direction. We will see ways of deriving that, but nonetheless, if let's say a simple case where there is metal sheets on the top and the bottom, the Young's modulus of that compared to the equivalent Young's modulus of the in-between core. I might use aluminum honeycomb to make it, but I will not use the aluminum's Young's modulus over there, because it is not bulk aluminum. It is just aluminum which is made into a particular shape of honeycomb. If you look at from the top, it's a set of honeycombs very similar to what the honeybees make. So that, which is why it's called a honeycomb. So if you look at that, it's not having material all over. So you will have to work through the geometry to see what actually happens when you apply a certain force, therefore a certain stress, or how much of deflection it has, and therefore how much of equivalent strain, and therefore you have to calculate that E, which will not only be a function of the material property of aluminum, which is used to make that honeycomb, but also of that geometry of the honeycomb in terms of its sizing, etc. So that will also bring in an equivalent E for the honeycomb, as if instead of that hollow structure that we have over there for the core, if it was solid, an imaginative material, and what we call as an equivalent homogeneous material, it would behave in a similar sense as far as the structural behavior is concerned. So that's how we derive the E. So that E for that aluminum honeycomb will be much, much smaller compared to the E for the top and face, which are bulk materials that you have. So the E will be kind of scaled down by a geometric factor for the honeycomb, and therefore that will also be a small parameter. So when we do either a plate model for this, which is a dimensional reduction, or a beam model for this, which is also a dimensional reduction, we will have to take advantage not only of the overall geometric small parameters h by b, b by l, we should also take advantage of t by h being small, E of the core, let's say EC, being small compared to E of the face sheets, EF. So EC divided by EF is a small parameter, T divided by H is a small parameter. Just like for any beam, you would have the H and B small compared to L, therefore H by L and B by L are small parameters. So these are things that I'm taking advantage of the kind of situation that we have over here to introduce certain concepts which will be useful for future classes. Purely from this slide perspective, that is the stiffness based design, all of those details that I talked about are not of great significance. So as I said, when you're doing a stiffness based design, there are two reasons you could probably be doing it, either both or one of them more important than the other. One is that you want to keep your static deformations as low as possible. The second is that if it's a dynamics problem, you want to make sure that the natural frequencies are as high as possible beyond a certain range in which you expect the loads to be at in terms of their dynamic ranges, their frequencies at which the loads come in. So whether it's to bring down the deformation or to increase the natural frequency, it is the same parameter which comes in, but a slightly different form as far as their power is concerned, which is what we will see. We will focus on the dynamics for now. The static is quite simple, very similar to what we saw in the previous slide. So we take this example of a cantilever, which is thin-walled in the sense that the face sheets are thin compared to the overall thickness. So thin-walled sandwich beam is what we have over here. The faceplate thickness, as I said, T is very small compared to H, which is why T by H is very small compared to 1. And then we also have that the core is made out of a much more flimsy material. It could be a foam, it could be a honeycomb, but either case, your mass contribution from the core is much smaller. And of course, if you're looking at the axial stiffness, that's also much smaller, but it does offer substantial transverse stiffness, which is of no concern for us here, because the load that we are applying is a moment. There's not going to be any transverse shear actually in this problem. Now, the moment of inertia about the neutral axis in parallel to x2 direction, which is parallel to the B2 vector that we introduced in the previous slide. So same coordinate system, if we take that moment of inertia I2 is going to be equal to just the area of the face sheets cross section, which is the breadth times the thickness, and there are two of them. Assume for symmetry, let's say for simplicity, both are, it's a symmetric cross section, therefore top face sheet and bottom face sheet are both of the same thickness T instead of T1 and T2, which is normally the case. So you will have two of those BTs from the top and the bottom, and then the distance they are from the neutral axis, in which case this case is just the geometric center, and which is along your x2 axis or your parallel to your B2, and therefore that distance is h by 2 approximately. Even if you take the overall thickness as h, because T is very small, I don't need to subtract h by 2 minus T by 2. That is what it should be in reality. But because T, already I've said T is very small compared to h, I can ignore that h minus T, the whole thing divided by 2 instead, and put it as h by 2 whole square. So this is the moment of inertia, and the reason it is important is the bending moment is what we are applying. And the mass per unit span, once again very easy to see. Already we have said not only is the stiffness of the core very small, the density is also very low, and therefore of that equivalent homogenized structure, because there's so much of hollow. You can think of both the phase sheets made out of aluminum alloy and the same aluminum alloy being used for the core as well. Very easy to see that these are bulk materials for the phase sheet. The density is same as the density of the material, whereas here it has to be that volume fraction of how much the aluminum is actually occupying that space divided by the overall volume of that core, which will be very small, and therefore for the mass I can take just the mass of the phase sheets alone. Two phase sheets, so two of them of area BT, and we are talking of per unit span, so along the length. So I'm not taking L into account, otherwise the volume will involve BTL for each phase sheet. So for each phase sheet it is BT, for two phase sheets it is 2BT multiplied by the mass density of that particular material that we are looking at. So it is 2 rho BT. Yeah, we are because it is eventually what is important is the good question you brought out. Purely from a mathematical perspective, when you're looking at the moment of inertia, that will also make a reasonable contribution, especially because h is very large compared to t. But what we are interested eventually is not in I, but in EI, which is essentially a weighted EI, because E for the center is very small, so that will weigh it down. So good that you brought up that question. Purely if I'm looking at I cannot say that this is all that is, but keeping in mind that eventually I want to calculate EI, therefore I'm looking only at that part of the I. So next, the first bending, again, this we will give without proof, because we are not at a stage to derive this right now, but essentially very similar to what I talked about, a single degree of freedom system where you have a square root of k by m, which is the spring constant divided by the mass. So here also you have something very similar to that. You are having a EI by m, where m is of course the mass per unit span over here. So and it's proportional to 1 by L squared. This is very similar to if you look at the Euler buckling kind of a formula where you have pi squared EI by L squared, very similar to that, but that is essentially stability problem. Here we are looking at a stiffness or a dynamic problem, but very interestingly, we will see later on and revisit this, the behavior of certain materials and structures, especially beams and shells, with respect to space. There is a beautiful analogy of how they behave with respect to time. So in other words, you can draw this analogy and you can see, if you understand one aspect well, very easy to translate that knowledge to the other, and the behavior with respect to time will be very similar. So that L square, inverse L squared behavior, what you observed in a buckling load, very similar kind of a thing you observe in as far as the natural frequency over here is concerned. So right now it may not be clear because you're talking of two very, very different things, like comparing apples and oranges, but later on when we actually go through the overall model, I will revisit this analogy and we'll talk a little more detail about it. There are many, many different levels at which that analogy works. So this is the first bending natural frequency, and your omega is therefore h by L squared into E by rho power half once you substitute for your m over there and the I over there. So from these two equations that you have, so once you substitute that, you would see that your omega, the natural frequency, is depending on two quantities once again like before. One is a geometric quantity in the first bracket, which is your h by L squared, and then there is a material property in the second bracket, which is a square root of E by rho. So this is what I was saying, there's a twist to the tail. If you're looking purely from a statics deformation point of view, E by rho is all that you would have looked at as a specific stiffness. But once you come into looking at design for dynamics, which is essential in many situations, you will have over half. And the reason why this is important is, for example, between two materials, the E by rho might be double, but if you're comparing for dynamics purpose, one may not be as good as double of the other. It might be only about 41% better, because square root of 2 is 1.41 approximately, so about 41% better is what you're looking at. Still better, but the margin of how better it is compared to the other will change once you bring in this factor into account. So then for a given geometry, we would have omega is proportional to E by rho power half as far as the material property is concerned, because we are dropping the first term, which is purely geometry dependent, H by L squared. So the material performance index for stiffness based design. So another thing that you're looking at is from a perspective of let's say buckling, you would typically want to reduce the length of a column or something like that. So when you do that, the critical buckling load will come down, but you would also have to be careful, because your natural frequency will also come down, and it could be coinciding with some of the load frequencies. So though we are looking at all of these in a compartmentalized sense, strength-based design, stiffness-based design, stability-based design, you have to take all of them into account, because many of these depend on the same parameters. In this particular example, we saw L, but there are quite a few other quantities also which are repeating across, including the thickness, etc. So we have to ensure that all of that is accounted for. Okay, any questions on this? Okay, let's go into the third one, and probably we'll take up the third one next class. But this is in lieu, just before introducing that third criteria of stability-based design. This is when we were having just online classes a couple of years back, the same course. I gave this as a quiz on Microsoft Teams. We had a much bigger class. We had about 43 students over there, and the responses that I gave for a question which is a multiple choice question, but where not one but more than one answer could be right. So this question was asked that which of these situations which are mentioned below in terms of different kinds of structures as well as the loads that are applied on that, which of these situations can lead to a compression, a potential compression, and therefore because compression is there, it can lead to buckling as well if the load is sufficiently large. The load in some case could be a bending load, a transverse force load, whatever that is, distributed or concentrated. If that is increased beyond a certain point, is there a possibility of buckling occurring in some of these situations? And these are the number of students who answered for each one of those criteria over here with the color code over here. So, so one or more answers could be right, as I said. And as I said, the class strength was about 43, about 36 respondents were there. So almost all of them except one probably chose this one, which is quite obvious. When there is a column under compression, there is a situation where the load is reached large enough to buckle, if and only if, of course, the material failure has not happened already. In other words, the stress at which the buckling happens is lower than the compressive ultimate strength or yield strength of that particular material. So considering that, there is a possibility that this can undergo compression. But I was kind of pleasantly surprised that there were positive answers for these as well, because unlike for this class where I talked about this quite at the beginning, where we talked about, let's say, the torsion problem, where we saw that there is a particular direction in which there is compression, etc. I had not talked about all that at that stage of the class, and still quite a few of them answered positively for the others, which many people would have probably ignored. So this is a panel under pure shear. Very clear that this tabletop, for example, a panel under pure shear. Suppose I'm applying a shear over here like this, and again at this end, if I apply a shear over this like this, it's quite clear that these two, this diagonal is getting compressed and this diagonal is getting extended. So there is a particular direction along which there are compressive stresses which are developing, and therefore along that there is a possibility of the shear occurring, so the buckling occurring. So in fact, we I think in the first or second class we discussed this with the Mohr circle and all that. So I think you're familiar with that. Same thing, shaft in torsion. essentially turns out to be a panel because it's a thin wall tube usually you have, and that is essentially under pure shear. So because of the same reason, you have a shaft in torsion. Whether it is thin wall like that or even a solid shaft, you could have a possibility of buckling occurring over there. Then a beam in pure bending. Once again, many people will think there's no force over there. There's only a moment, but still in the presence of, in this case also, in fact, it's only a moment. It's a M1 according to the coordinate system that we introduced. This could be either an M2 or an M3. So beam under pure bending, very clearly, one half of the beam is going to be undergoing tension, the other half is going to be undergoing compression. So that compressive portion can undergo buckling. So the confusion usually is in the sense that wouldn't the tension part of the beam avoid the compressive portion from getting buckled? So in essence, what we are saying is, what we are talking about here is some kind of a localized buckling that is happening rather than a global buckling. Whereas in this case, it's very clear it's a overall entire beam is buckling. Whereas here there are portions of the beam which are buckling, and it's very evident in the case of the spar. If you take the spar, for most of the time in the flight, the top flange of the spar cap on the top is going to be undergoing compression. So there is a possibility that there is if the loads reach large enough, that will buckle. But obviously you want to ensure in the design that you have designed it such a way that that will never buckle. You will allow the skin to buckle, but you'll never allow not only the spar caps, but even the stringers. You will ensure that they don't buckle, because they are the ones which are going to take most of the load which was being taken by the skin beyond buckling, that is in the post-buckling regime. So keeping that in mind, it's very important to bring that distinction between global and local buckling that is happening over there. And even that local buckling is a kind of an instability, though it's not happening at the overall component level. And then, so that's pure bending. And these two cases, whether even if it's not a pure moment, whether it's a transverse force, concentrated or distributed, once again you have a bending moment at different locations. Bending moment once again causes compression half of the beam, either above or below the neutral axis, and those regions are susceptible to buckling when the load, in this case the transverse force, distributed or concentrated, is increased beyond a certain level. Once again, all these assuming that material failure in those respective situations has not yet occurred, and this occurs before that. Therefore, there is a possibility of buckling happening over there. So I think we'll not have enough time to complete if we take up the stability criteria. So we'll take it up in the next class. Thank you. If there are any questions, I'll be happy to answer that.